Got another walkthrough for you. This one is on astronomy. Okay, so this says the mean intensity of solar radiation arriving at the sun is 1.37 kilowatts per meter square. The distance of Earth from the sun is 1.5 times 10 to the power of 11 meters. Show that the intensity of the sun is about that much. So I want you to solve this and I'll show you the answer. Okay, so we have the radiant or measured flux intensity, which is basically the intensity of light arriving at the Earth, which we resemble with I. And then we have the luminosity of the star. And we know this is linked by the formula I is equals to L 4 pi d squared or r squared. Okay? It's better to write that as d. So 4 pi d squared. Okay? So now what we can do is we have to find this L. So we can just multiply this with the intensity. And we'll get our luminosity as 3.87 times 10 to the power of 26 watts, which is approximately the value they gave in the question. The next part says the energy radiated from the sun results in a decrease in the mass of the sun. Calculate the decrease in the mass of the sun due to the radiation over 1 year. So basically sun is going to release a lot of energy, and that energy is, if energy decreases, the mass will also decrease. So we have to find this mass decrease. Okay, now they give you 1 year is this much time. We know power is energy divided by time, and we already have power, which is the luminosity, and then we already have the time given to us, 1 year. So I can simply multiply power and time to get my energy, and both power, which is basically the luminosity, is given to us, and the time value is also given to us. So 3.87 times 10 to the power of 26 watts times 3.15 times 10 to the power of 7 seconds gives me 1.22 times 10 to the power of 34 joules. So this is my energy. Now I know E is equals to mc square, where change in E is equals to the change in mass C square. So if this much energy is released, how much mass would that need to decrease? So I can just plug in the energy value, and I have the C square, and I can move it to the other side and divide 1.22 times 10 to the power of 34 joules with 3 times 10 to the power of 8 square, which is just speed of light, and I'll get my mass as 1.36 times 10 to the power of 17 kg, which is the decrease in mass of the sun every year. The astronomer Hertzsprung used parallax to determine the distance. The variable star Alpha Cephei is 4.6 times 10 to the power of 17 meters from the sun. Deduce whether the distance of Alpha Cephei could be determined from the parallax measurements, and they've given the distance to the sun from Earth. So we know when we use trigonometric parallax, we're going to measure the other star from the backdrop of the background stars, and we're going to see how the angular displacement is based on Earth's movement 6 months, and we know that we have this as the distance of the Earth and Sun between them, and this is the movement of the Earth in 6 months time, and we can use this to measure the angular displacement, this angle. And what they've given to you is they've given you the distance between Earth and the star as well, and they just wanted to find this theta. Okay, so I can just say tan theta is equals to the distance from Earth and the sun and the distance from Earth and the star. And I can just find theta as this value, which obviously is much bigger than this much value. Okay, so what the question says is, using parallax measurements, astronomers can determine distances with all the stars that have a parallax angle larger than this much. And we can see that this angle is larger. So yes, we can determine the distance. So here's a complete summary of the answer. It's basically basic trigonometry and just a bunch of stars, so you can pretty easily solve this. Cepheids are a type of standard candle. Describe how standard candles can be used to determine the distances to stars. It's 3 marks, so you can try it and I'll show you the answer. So first of all, a standard candle is a star with known luminosity. Example, Cepheids and type 2A supernova. This is the extra point right there. It's not really an answer. Okay, but often this will come in exams just as extra information for the question like we just had right now. So it's good to know that these two can come up in exams. So this gives you 1 mark. Then intensity, we're going to measure it. So that's 1 mark. And then we can use this formula, which is intensity is equals to luminosity divided by 4 pi d squared. And I'm going to make this d my subject. So here I have my subject. And using this, I can find the distances to stars, where I can find d value, and that's the distance to the stars. Okay, that gives me my 3rd mark.